morning, Precalculus. Welcome to Tuesday, May 12th. Today we're going to be talking about parametric equations. So we've been talking about vectors, and now what we're going to be doing is talking about parametric equations, which are equations that are now, rather than being just an x versus y, you have the idea of you have your time versus your x versus your north. So you basically have t, x versus t, and y versus t. So you're going to be doing some stuff where it works similar to vectors, where you have your sort of comma notation between two different things, where you have x direction, y direction, but instead of relating x and y to each other, you're going to be relating them to the variable t. So in a sense, what we're actually doing is we're graphing in 3 dimensions, time being one of the dimensions and the xy plane being the other 2. So with this, to start us off, what we're going to be doing is we're sort of in a weird, bizarro world where it's Gotham City instead of Gotham City, and we have Evil McFreeze rather than Mr. Freeze. So what he has just committed a heinous crime of unknown magnitude, and someone has managed to get a radio transmitter onto his vehicle that can track his position from a distance every 10 seconds. So what the first thing that is going to be done is, if you look over here, we have a chart that has time, feet, east, feet, north. And what you're going to do is you're going to, on a graph, you're going to do, make something of suitable scales, sort of dotting these points and then labeling them by the time. So you'd start off with 600 feet east, so 600 on your x-axis, and 1250 on your y-axis, and that would be 0.0. And I'm going to give you a moment to draw this because I have done this, and I'll show you sort of what the result should look like for that part. So I'm going to pause the video here. And as you see here, this is what your graph should end up looking like as you sort of create the points. You'll see you have 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And so we have these points. I decided to draw a blue line to sort of designate these points. And here's sort of the table rewritten from here just to make it a little bit easier for me. Is something I did. And I made this graph in Desmos. Unfortunately, you can't do a table with parametric equations in Desmos, which kind of sucks, but that's all right. So, within this, one of the things that we did is we need to now sort of discuss how does the motion, how does this sort of show the motion of the car? How would we describe the motion? And with that, what we really need to be focusing on is how the position changes over time. So, in my mind, if we look at this, we start out, and it looks like we're heading straight south. And so I'd say, well, we traveled straight south. Mr. McFreeze, Evil McFreeze, traveled straight south, and then he went due east. And then at some point he went southeast. So, straight down, straight to the right, and then southeast. And later on, it says, at one point in time, McFreeze made a right-angle turn. Where and about what time? Well, if we look over here, it's kind of obvious that he likely made a right-angle turn. It's not 100% guaranteed that he made a right-angle turn, but I would assume that the road, you have a city, there's probably going to be a lot of right turns available, or square turns. And somewhere between 50 and 60, he made a right turn and sort of started going towards the east. And then from there, what sort of goes on is he continues on, and then he sort of goes diagonally. And so this is sort of a first-time introduction to the idea of parametric equations. So we mapped a person's position in an xy plane versus time. So in a sense, we have parametrized his motion based on time. So we have a direction we're sort of going, and we separate it out based on time. Now, the next thing that we sort of go into is sort of understanding we have this map of these directions based on time. Another thing is, if you look at 10-64, I know you guys can't really communicate with your group, with your team, but basically, if you think about it, this is something that was probably covered in physics. The idea that the horizontal motion of a projectile and its vertical motion are separate. Now, this is true. So if you were to, say, flick a quarter off the edge of a table versus just sort of drop one, they should both hit the floor at approximately the same time, or pretty much at the same time. And they definitely would if it was in, say, a vacuum. So with that, using this idea that you can separate both the horizontal and the vertical, it makes it very straightforward and very easy to sort of utilize when it comes to parametric equations for things like, say, a seagull dropping an oyster shell. So in this one, in 10-65, what we do is we have a seagull dropping an oyster shell, and there's wind blowing the shell sideways at 15 miles per hour, which is 22 feet per second. So what we're doing is we're creating an equation, x equals 22, which is sort of important because what's going on here is we're going to be creating two equations, y of t and x of t. So 65, we have x of t equals 22t. Now what this means is that every 22, like every second, the shell should be moving 22 feet. Now this isn't 100% accurate because of the way air resistance and all of that work, but we're going to call it pretty much good enough for right now. And so our equation for our x coordinates, so how far it's moving in the x direction, is based on this. And since it's being dropped, our direction in the y direction, our y of t, is going to be negative 16t squared, which is sort of the effect of gravity on it, the acceleration due to gravity, plus 256. Now the 256 is sort of its starting height because he's on top of a pole that's 256 feet above the ground, which is lovely. And now what it wants us to do is in A, it wants us to make a table based on these two things between 0 and 4. Now it already has part of the table, and so what you would do is just sort of fill it out the rest of the way. And then what you're going to do is create a graph similar to the one you have done in 63. And further on, you're going to end up just sort of making some changes and sort of trying the graphs at different speeds, just sort of changing your x of t. So rather than it being 22 feet per second, maybe it's 10 feet, maybe it's 40 feet, and so on and so forth. So what you're going to be doing is sort of making those changes and sort of seeing how it ends up working. Which is kind of an interesting fact. It says 10, 30, and 30, 10, and 5 miles per hour. Don't consider that as miles per hour, but as feet per second, so you don't have to do any other crappy conversions. Because it's kind of a pain in the butt to convert from miles per hour to feet per second. And what you should notice is by doing all these, that as you change your x of t, your y of t is staying the same. So what should happen is, no matter what, each of these oyster shells, depending on the wind, would end up hitting the ground at the same time. And all that would change is just how far along the x-axis they end up during that. And with this, what I'll do is I'll actually take a moment to sort of show you on Desmos how this kind of looks. Now, as you can see here, what ends up happening is you have your different equations based on the models that you were sort of drawing. And as you can see, you have basically the y coordinates are the sort of parametric equation of the y coordinates are all the same, and all that changes is based on the wind, how far the oyster shell moves in the x direction. And it sort of ends up being similar shapes, and based on the same parameters, the same sort of range for t for your time, they all end up hitting the ground at the same time, and all that changes is just how wide or narrow this parabolic arc is. So that's sort of the big idea here. And then what's going to happen, so you'll sort of finish those up, and then what you'll do is you'll sort of continue on to doing 67, and that'll be the end of what you have to do today. I encourage you to sort of graph these by hands. Tomorrow I'm actually going to go in a little bit more detail of how you do these graphs on Desmos, but you can actually graph these on Desmos. I encourage you to do a 0 to 300 scale on the y and about a 0 to 150 on the x for this particular graphs, so then when you graph them all, it fits pretty well and you get to see all of this rainbow going on. So that's it for today. I hope you all have a good day, and feel free to hit me up with any questions.